Hey, this is Abdallah Duras,
I'm Cole Berger.
And I'm Will King.
and we are here to bring you the third and final report on our BRG.
So our team was tasked with developing a Rube Goldberg type machine that would reinforce educational principles in the classroom. We decided to focus on high school physics students, and these students we figured would be in 11th and 12th grade. With these basic ideas in hand about what we wanted to accomplish with our BRG, we developed a mission statement, as you can see here, and this gave us some more clear ideas as to what we needed to accomplish in our design. One of these things was that our primary market would be to high school physics teachers, as they would be the main people facilitating the use of the BRG, while the end users would mostly be the high school students who are reinforcing what they had learned. Also, with this, we made some basic assumptions about the people who would be using our BRG. One of these would be that they would have a basic understanding of physics topics so that they would be able to fully understand and use our BRG. Also, we assumed that they would be able to use basic tools to assemble the BRG so that it could be used. Okay, so next we're going to talk about project management. Here seen in our Gantt chart, this outlines all of the tasks that we needed to accomplish throughout the development of our BRG, and this was done over 3 design phases: DP1, DP2, and DP3. In DP1, we focused on a lot of idea generation. So here we looked at many of the basic ideas that we as a team had and how we wanted to implement those in our BRG. So in the different stations, what topics we wanted to cover and how we wanted to solve those problems. We also performed some basic economic analysis. So we looked at how much we thought the product would cost, and then in turn, how many we would need to produce in order to turn profit. In design phase 2, or DP2, we focused on building initial prototypes and developing initial CAD models so that we could see how the product would work. We then continued performing economic analysis, and here we looked at how much of a loan we would need to take out from VTEPs in order to aid our product development. And then in design phase 3, we looked at a lot of the fine details of our design. So we built a final model, we looked at a lot of industrial design, product architecture, and we performed final economic analysis. So here we looked at the specifics of how much the product would cost and what we would need to sell it for as well.
So for customer needs and product specifications, we surveyed several different people who use similar physics-themed educational products. And our goal with the surveys is to translate customer needs into product specifications. So this section gave us a good idea as to what we need to address, what we need to refine, and what we need to completely avoid when making our BRG. And many customers complain that the educational products that they're using do not last very long and they break easily. So our translated customer specifications is to create a BRG with sturdier material that will last the user a longer time. And many customers also complain that the products that they use are limited to like only one topic, so they get bored with the product after a little time. So we made sure that the 3 different stations convey different physics concepts so that the student could get as much as they can from our BRG.
So next we created the CAD models for our BRG, which are seen here, all assembled into one giant assembly of all of our 3 stations. Here you can see our station 1 is colored black, station 2 is colored gray, and station 3 is colored white. So the way that our BRG works is our ball travels down the initial ramp and then rolls around this little curved section and into our connecting elbow. And then the user is going to slide that piece into the fan base, then turn on the fan by controlling it on the Arduino Valley computer. And then once the fan is activated, the ball will shoot up through the clear tube and into the funnel. Once it lands in the funnel, it enters station 2, where it rolls down the launch ramp, and then the user will position the catch ramp so that the ball will land perfectly in it and then roll down into station 3. And then once the ball is in station 3, the user will pull back the plunger, and then the plunger head will hit the ball through the loop and into the end of our BRG. So once we had our CAD models, we were able to come up with a product architecture for our BRG. And then that product architecture is implementing both bus modular architecture and slot modular architecture. The main bus of our BRG is the pegboard, and then all of our 3 stations implement slot modular architecture, and they all rest inside the pegboard via pegs in the bottom of each component. And then for our station 1, the fan base has both the fan base lid and fan and the connecting elbow and tube connected directly to that fan base. And then for station 2, the support rods connect directly to the pegboard and then individually to both the catch ramp, catch box, and top ramp. And then for station 3, we have our plunger box and the loop connected directly to the pegboard, and then the plunger arm and plunger top connecting directly to that plunger box. And since we have all 3 stations as individual components, if in the future we were to come up with more stations, we could easily set them on the pegboard and they would act as their own separate components. So next we looked at the industrial design for our BRG, and here you can see in this infographic we looked at both the aesthetics and ergonomics of our project. And for the aesthetics, we definitely wanted to make our product stand out a tiny bit, but overall that wasn't our main concern. We definitely wanted to focus more on the ergonomics and how the user will assemble the product. So when looking at that, we definitely want our user to assemble the BRG pretty quickly, and also we want our safety to be really high so that the user won't have to worry about getting injured while using our BRG.
In product decomposition, we created different solutions based on 5 different criteria: initiating station, construction material, assembly, connection to board, and the ball movement through the board. For each different criteria, we had different weights based on what we believed would be the most valuable thing to the customer. So we had construction material as the highest weight because a sturdier BRG is going to last the customer longer. Then we rated each different solution based on these criteria and used that to determine which solution is viable and which needs to be let go. Then we rated the designs using the concept screening table, which is a quantitative method, and a concept scoring table, which is a qualitative method. We looked at one of our solutions and picked it as a baseline, and then we ranked other solutions based on that baseline. And then we repeated this method for stations 2 and 3 to come up with 3 different solutions that we believe would be most viable to use.
All right, so now we're going to look at the economics of BRG. So in this phase, DP3, we looked at the specific cost of the BRG to produce it and then what we wanted to sell it for. So here you can see this is our cost sheet where we looked at the individual cost of each component of the BRG. The majority of the pieces we used injection molding for. However, there were a few electronic components. So this would be the Arduino board and some of the other wires and pieces associated with it that we wouldn't be able to injection mold. So we bought those in bulk, and those came out to a relatively low cost. The other pieces, however, we decided to use injection molding for because over time that would be the most cost-effective option for how to produce those. All of the pieces we used polyethylene for, except for the clear tube that would be used to launch the ball up from the fan, and for that we used clear polycarbonate. After looking at all of these pieces, we ended up with a total cost of $25.77, and then after profit and overhead, we ended up with a final cost of $70, and that's what we would sell the BRG for. So the overhead came in at $44.23, and that would be approximately 71%.
So for future changes, we are going to discuss the mistakes we've made, improvements we can make, and upcoming plans. The team has decided that injection molding is most likely the most cost-effective way to mass produce our BRG if we were to do so. As for the troubles that we had while creating our stations, the connection of the stations to the pegboard was difficult. So future teams, if they were to replicate our design, could keep that in mind in the design phase. Moreover, the ping pong ball movement through the stations was kind of difficult. So even though we came up with a solution, we figured that pointing that out would be essential in future designs. For product specifications, future engineers could survey physics students that are in high schools about what physics concepts that they're struggling the most with. And so they could develop BRG courses that convey those physics concepts. Also, they could talk to physics teachers and see what physics concepts they have the most trouble explaining and when a study aid or a visual could be beneficial to the students. For the upcoming plans, the team is putting together a BRG instructions manual so that physics teachers could build their own BRG. And aside from that, our BRG has concluded, and thank you.